So yeah, let's just dive right in. Who am I? As I said, my name is Ilja. I'm just gonna take this out. I have been using C for over 20 years, roughly about half its lifetime. I've written some C code over the years, but I've read a lot of C code. That's also because my daytime job, I mostly spend my time reviewing other people's C code. I try to estimate how much I've seen in the last 25 years. Couldn't really pin down a number, but it's in the millions, so I've seen some C code. I like C. I like it a lot. Up until very recently, maybe a year or two ago, it was my go-to language. And it's been my go-to language for a very, very, very long time. So huge, huge fan. But I do realize that there's some things that that are wrong with it. I'm also a security guy, and like there's this saying, to a carpenter everything looks like a nail. To a security guy like me, everything looks like a security problem. So I'll be talking about security, especially once we get to sort of the second half of the presentation. Once we sort of get halfway-ish through the history, we'll dive into some security stuff. So what does this talk about? Well, I think the title's fairly self-explanatory. My agenda is essentially, I cover some history and some facts. I've tried very hard to be accurate, but the thing about history, even recent history, is that it's sometimes not always easy to get everything right. So if there's inaccuracies, there might be some inaccuracies in here, but as I said, I've tried really hard to get the facts right. It's based on interviews with people. It's based on email exchanges back and forth. It's based on credible articles, stuff like that. So I think I got most of it right, but I can't guarantee that there's not an inaccuracy in there somewhere. This is then sprinkled throughout with some personal opinion and observations. And I will end the presentation with what's next? What does the future look like? We've had 50 years of C. Should we have another 50 years of C, right? Let's try to get some answer to that question. The good news is this presentation is not deeply technical. There's a little bit of code here and there, but it's quite broad. So that means the audience doesn't have to be like these hardcore C developers, although if you are, this might be interesting to you. But if you're interested in computer history, if you're generally interested in programming languages or their history, if you like systems programming, if you like security, basically if you're a nerd or like tech stuff, you might find this interesting. So let's dive into like a one-slide history, and then I'll spend a little bit more time diving into taking a little bit more time to cover some history. But the very short history, like the one-slide history, is basically this, right? C is very, very intricately connected with Unix, right? Unix took, quote unquote, some inspiration from Multics, which was an OS that was written before Unix. And this was written in a programming language called PL1, which is one of the quoted ancestors to C. Although it's not the main one, it had some influence on C and languages that came after it. For example, the C comment style / asterisk /, yeah, that came from PL1. All of the stuff I'll be talking about was initially created at Bell Labs. I think most of that happened in New Jersey on the East Coast. We're talking late 60s, early 70s. And after that, we'll dive into 80s, 90s, and so on, which is sort of everything that springs from it. And sort of the key players, certainly in early history, are one of the guys that was in the picture on the first slide, Ken Thompson. He created Unix, and he created the direct predecessor to C called something called B, which we'll dive into in a minute. And then there's Dennis Ritchie, who is the guy who actually created C. Unfortunately, he passed away about 11 years ago, way, way too young. Absolute genius, and he was recognized for the cool things he's done, although not enough, I think, but still. Another interesting player is a guy named Brian Cunningham, who is one of the authors of the book, the C book. He was not actually involved in creating it, but he wrote the book, and he wrote some other interesting languages. One that is kind of sort of C-like. So if you like awk, the K in awk stands for Kernighan, right? So this man does know what he's talking about, even though he may not have invented C. He was certainly around that area, clearly understands it very well, was there when this stuff happened, and built other languages that sort of took some inspiration from C. And then, even though this talk is not about Unix, because C is intricately connected to Unix, there will be some Unix stuff in here. And so there's other interesting people in here, and I could have done a long list, but I just finished my slides and I didn't get to this part. But other ideas and code from people that I should mention is Doug McElroy, who in his 90s, and I think he's still alive, but he's usually the forgotten person when people talk about Unix. But a lot of the ideas, he had something to do with it. For example, pipes. He was involved in some of the stuff with pipes and a bunch of other things. And then there's ... Dozens and dozens and dozens of people at Bell Labs did some really cool stuff that applies to C and applies to Unix. So with that, let's dive into before C was created, the ancestors. So we'll start in the 1960s. We could start before 1960s, but I only have 45 minutes, and I figured I should start somewhere. So let's start with Multics. Multics was an operating system, the design of which started in around the mid-60s. This was a massive, massive operating system design for a massively large computer at the time. And this was, Ken Thompson described as sort of the second system syndrome, because it started at MIT, and before that they had done an operating system called CTSS, the Compatible Timeshare System. And this was like the next bigger, better, bolder, stronger, faster version of that. And so it was very elaborately designed, and there was a cooperation between MIT and Bell Labs. And MIT did the design and some of the coding, and then Bell Labs did most of the coding, and then GE, General Electric, was going to build the hardware. Amongst the teams of people from Bell Labs that were involved in this stuff was Ken Thompson, right? So there's a great video from I think 2019 where Brian Cunningham and Ken Thompson kind of talk about some of this, and essentially, Ken described it as over-engineered, late, too big, delays, and so on and so on. And what happened is about a couple of years in, by 1969. Bell Labs was like, compiler's not ready yet, this thing is moving too slow, it's too big, we are so done with this, and they just pulled out. And so if you see that talk, and so if you talk to, or see comments from some of the people from Bell Labs around that time, Multics is seen as this huge, massive failure, because it was late, and it was big, and it was over-engineered, and all those kind of things. But it did eventually ship, 10 years later, 1975. Depending on who you ask, it actually did become somewhat moderately successful-ish, in that most of the commercial entities probably didn't lose money on it, but I don't think anybody got rich off of it. The other cool thing about Multics, so it was decommissioned in 2000. But what was really cool is that a few years ago, the folks that owned Multics open sourced it, and a bunch of people wrote a hardware emulator for it, and the source code was compiled and built, and it runs on the emulator, and it is currently, as far as I can tell, maintained by a group of volunteers. And so that screenshot right there, that is Multics 12.7 running on my laptop. That's from about a week or so ago. So if you want to play around with Multics, you can. But this Multics kind of sets the stage for everything else that is to come. Right? So Bell Labs pulls out of Multics, and Bell Labs is like, we're done with operating systems. This was a horrible, horrible experience. Never again. Ken, however, was like, well, I kind of like operating systems. Like, that was a failure, but like, I want to build another one. He, Bell Labs at the time was a very big place, and went around and found this really, really small computer called a PDP-7 that no one was really using. So a very small computer even at the time. It had what they called 8,000 words of memory, which isn't much. It's what 16-something thousand bytes of RAM that's available. So even for at the time, very, very small computer. And he had this really large disk that was attached to it. And when I say large disk, I mean the disk was as big as me. It's like a big, big giant plate. And I think there's a picture of it somewhere. And it was hooked up to the machine. And Ken basically wrote a scheduling algorithm for the disk, and it worked. But he needed to write some other code to test the disk, see how well the algorithm works. And so he wrote a bunch of programs and games and so on to test the disk. And as he was doing this, at some point he realized all the programs he had, and he goes, I'm 3 weeks away from a whole operating system. So he said, I need an editor, an assembler, and a kernel. Which, it's insane. Anybody can write those 3 things in 3 weeks, because that would take me years. But that is, I mean, that is the spirit of the time, and it shows you the genius of Ken Thompson, who, if you don't know him, you may know some of his other work. He was one of the designers of the Go programming language. He was also one of the folks that invented UTF-8. So he's had influence in a lot of places for a lot of stuff we use. But this is sort of the history, the beginning of some of these things. So anyway, he took 3 weeks, wrote an editor, an assembler, and a kernel, did it all in PDP-7 assembly, and Unix was born. This was 1969. This was in a very old, crummy, sort of abandoned PDP-7. There's a whole story about him wanting a bigger computer and it not really getting accepted. And so then he found some other teams that gave him access to some of the machines they were going to order. I think the second one was a PDP-10, but I'm not entirely sure. And that was for some of the folks at Bell Labs that wrote patents. And so he ported Unix to that machine. Again, that was a port entirely done in assembly. So that was the first port of Unix. And then at some point, they got their hands on a PDP-11 around 1960. Still handwritten assembler, took Unix and imported it from the PDP-10 to the PDP-11. This was the second port of Unix, still all done in assembly, right? So now we entered the 1970s. So this is, now we get Unix, right? And this ultimately evolved into, kind of what we know, right? I know this is a Unix system. So, we get all these new Solaris and HP Unix and Minix and Linux and Mac OS and so on and so on. I mean, there's this by the way is an image of the, I think System 7 Unix. This is DMR. That's Dennis Ritchie. That's the guy that invented C. But obviously there's, others. I mean, there's a gazillion different versions of Unix out there, obviously, right? And again, this is not a Unix talk, but they are related. So I do have to say something about Unix. But anyway, so now he's got Unix running on the PDP-11, and Ken's thinking was, no computer is complete without a Fortran compiler, right? I need a Fortran compiler. So he starts writing a Fortran compiler, but Fortran, I guess, was a relatively-ish large language at the time. And so the Fortran compiler he built was about 10 times too large for the memory for the PDP-7, because the PDP-7 had 8,000 words, but it was cut in two, where the 4,000 were used for the kernel, and then 4,000 are used for user. All of user, right, gets 4,000 words of memory. And so what Ken started doing is started cutting it down and cutting it down and cutting it down, and taking influences from other places to try to get some language working, right? Ultimately, once it started working, it wasn't Fortran anymore. It wasn't anything close to Fortran. It became something very, very different. It took inspiration and was much closer to another programming language called BCPL. BCPL was created by a professor called Martin Richards, who I think is also still around. This was created in 1967. This is a professor at Cambridge, but he spent a little bit of time at MIT at around the same time when the Bell Labs folks were doing Multics at MIT. And so they met and they figured, and they learned about BCPL and they understood BCPL. And so that BCPL and then a little bit of the PL1 for Multics kind of influenced sort of this B programming language that this thing eventually turned into. And there's actually a manual on the B programming language, and it says that B is a computer programming language directly descended from BCPL. It is running at so and so and so. B, compared to BCPL, is syntactically rich in expressions and syntactically poor in statements, right? And so the stuff on the right here, this is actual B code. And for those who can understand and read and recognize C code, it looks a lot like C code, but it's not exactly. It's missing some things. And we'll get into the stuff it's missing because, well, that's how we get into C. So what happened is Dennis Ritchie saw this, and he had access to some more powerful machines, and he wanted to port B to more powerful machines, and then started playing around with that. And so he started calling it New B because he started adding features to it. And at the same time, Ken Thompson was like, I've done 2 ports of Unix in assembly. We should really try to rewrite Unix in a more portable language. Let's try B. And then that was a huge failure. And then, at this point it was new B. They tried again, and it was a huge failure. And they failed 3 times before they finally landed on something that worked. And so every time it was this evolutionary cycle. It's like, I need features that like the language doesn't have, and it becomes an utter failure. And so ultimately, the big feature that made Unix work in high-level language was structures, right? The moment structures were added to new B, everything fell into place. And all of a sudden, Unix was written in a high-level language, and it was no longer assembler. And it worked. So basically, new B compared to C had structures, it had types, and it's byte addressable instead of word addressable, right? And there's a few other tiny changes, but those were the 3 big ones that sort of B, new B, right? And once you had a sort of evolutionary cycle, the 3 failures of Unix, and eventually you land on put these new features in, and new B isn't really B or new B anymore, so they say let's give it a new name, and that became C. Right? And so B and C are very, very similar, except for types and structures and bytes versus word addressable. Right? So now we are at C. New B is renamed to C. C was born. This is 1972. This was an evolutionary road to get there. Right? It was not created by committee. It was sort of organically grown. It was because of practical needs. Basically, C was created to build a portable Unix, right? And that gave it some interesting properties, right? Because it was a language that was specifically designed to build a operating system, but it turns out all the features you kind of got in C, you can't just build Unix with it. You can build almost any it's this sort of unique mixture of things that sort of inadvertently got into C. That work not just for Unix, but really if you were to do any kind of low-level programming, these are the tools that it gave you, and it did it better than anybody else, right? And then sort of by the time we get to sort of the late 70s, because these were all, they built a C compiler, but it was a C compiler for Unix. And by the late 70s, there was sort of the first portable C compiler, and sort of that branched off into sort of its own thing, and we'll get into that a bit more later. At this point, I kind of want to talk about, because we're now at the sort of the mid to late 70s, we're talking about some of the contemporaries to C, because at the time, and even a little bit before that, and a little bit after that, there were other programming languages that people build operating systems in. The thing is, most of this stuff either isn't around anymore, or it's very niche. It didn't stand the test of time, whereas C did. So if you look at the top, yes, we have assembly. It's still around for stubs and stuff, but almost nobody writes full operating systems in assembly these days anymore. It's very, very rare. I say very rare because there are some exceptions, but they are exceptionally rare. So what are the other ones, right? There's Fortran and COBOL, which obviously predates C by a good bit of time. This is, I think, late 50s, early 60s. They're not really systems programming languages, though, but they've inspired the systems programming languages, right? I mean, COBOL itself was mostly used for business logic. Fortran was mostly used for scientific calculations, but they have inspired others to do systems programming. Then there's what we've mentioned before, PL1 and its derivatives. So Multics was written in a dialect of PL1. PL1 was, in fact, designed by committee, by IBM. It was, for the time, a huge, huge programming language. Maybe the way we think of C++ being huge now, I think that's probably the way people thought about PL1 at the time, except it was spec'd and designed before there was actually a compiler. PL1 was used for some operating systems, mostly by IBM, because IBM created PL1. So the early AS OS 400s used PL1, but by the 90s, they switched to using C++. Their mainframe stuff still uses PL1 in a bunch of places, or PL8 or PL something, you know, some dialect of PL1. And then CPM, which is sort of an early OS for the microcomputers, think along the lines of MS-DOS, used PL1 as well. And then the other one is sort of the algol and derivatives. Again, algol, we're talking late 50s, and then you get algol 60. But there were a bunch of derivatives that sort of were at the time used for a bunch of systems programming. The one I mentioned here, MAD, is that one was used to write the compatible timeshare system. I don't think anybody has used MAD since. The cool thing is CTSS is open source, and you can actually look at this and see what it looks like. There's some other interesting things. Yeah, the ones I wanted to mention is a thing called SPOL and NOOP, which probably no one's ever heard of. But NOOP is still actively maintained, as far as I know. This is a algol-derived language that is used to create the MCP, the Master Control Program, and for the Burroughs mainframes. And now you might think, I don't know what a Burroughs mainframe is, but I know what the Master Control Program is. Yeah, exactly. Yes. It turns out one of the folks that worked on Tron, one of the technical people that gave information, was involved in Burroughs mainframe system, right? And so the Master Control Program from Tron was inspired by this the Burroughs mainframe's Master Control Program. And it turns out the Master Control Program was initially written in this language called SPOL, which later became NOOP. And what's really cool about NOOP is, I think that's from 1971 or so, is that NOOP was a completely memory-safe language, and it had a construct to declare unsafe code. This is C# does this, Go does this, Rust does this. But 50 years ago, NOOP started this, right? So this is a concept that we've had, and I wish C had this, but of course C didn't have this. But it would have been great if it did. It would have saved us a lot of trouble. Anyway, I wish it had more influence, but it was there, and it's still technically there. MCP is still something you can buy and use from, and it's no longer Burroughs. They got bought by Unisys, I think. But essentially, the MCP is still around. And of course, the other ones is Pascal. Some early Mac OS stuff was written in Pascal. I think Apollo Computers did some stuff in Pascal. So there were some operating systems written in the late 70s, early 80s in Pascal. But by and large, Pascal is a teaching tool, right? It's most. I mean, I learned Pascal in school. And then there's some others. There's a programming language called Bliss, which was used in bits and pieces of OpenVMS, and the early Amiga OS, I think, used Bliss. And then there's some, I think Ada was used for some, and this is, but now we're all 1980s already, so it's a bit past C's time. But these were the contemporaries of C, and I mean, none of these are anywhere close to being as popular as C is today or ever was, really. Right, so that's kind of my point, right? None of these ever attained popularity of C, right? Most of these are either dead or incredibly niche. Some of them were lucky enough to be brief enough to be popular for a brief period of time, but none of these were popular for 50 years, right? None of them stood the test of time. And this is where C stands out and shines, right? It somehow has this magical combination of things that make it absolutely perfect for low-level systems programming, right? Ken and Dennis just kind of stumbled onto this magic thing that, like, nobody's really been able to sort of recreate a similar thing. And it wasn't specifically designed for it. They just kind of stumbled over it because they needed it, because they wanted to port over Unix in a high-level language, right? But anyway, that's where we are. So in the 1970s, they port Unix to C, and then, it's like, you pop a cork from a bottle of champagne, and everything just comes out, right? It becomes available to universities, and these bright university students get access to it, and they start playing with it, and they go into the workspace, and they take Unix with them, and they take C with them, and that's sort of, that then leads into sort of the 80s and 90s, is where C and Unix becomes or at least C becomes very ubiquitous. And so when it comes to Unix, at Bell Labs, there were two very creative periods. One was 1972, which is where they did this initial creation, and they did the C and the port. And then in sort of the later 70s, where they demonstrate the portability, gets shipped to a bunch of universities, gets ported to a bunch of architectures. People start building compilers for this, both commercial and open source, as well as academic as a teaching tool, how to build compilers, that kind of stuff. And then lastly, in the 70s, the book, right? The C book, right? The first edition of the C programming language, right? Which to me, this book, although I've only written the second edition, and there's not that much difference, but there's some. To me, the C programming language is the single greatest book on programming, because C is a very simple language, and so it's some of the concepts it uses are difficult, but as a language, it's very simple, right? And so you can describe it in about 230 pages, and in fact, I think the first or second chapter is not even, it's a tutorial, right? And then it dives into the language, right? And in fact, as far as I know, the very first Hello World program ever was in the C programming language book. So anyway, that's how we get that's sort of the birth of Hello World program. If you've never read this book, I would highly recommend it. It's still on my bookshelf. I occasionally read it. There's some really cool stuff in there. Right. So now we get to the 80s. C gets around, right? It's now out there, right? These university students have graduated. They've taken it with them to their job. They're building compilers. It gets standardized. Endless stream of commercial Unixes. As I said, we're now at the point where there's a bunch of stable, reliable compilers for C, commercial, open source, academic for many, many platforms. Both C and CMLI inspire Stroop to create C with classes. This is the late 70s, but that then evolves in C++ in the 1980s. I don't really want to talk about C++, but I figured, there's some history there too, so let's at least mention that. 1980s also when Ken Thompson does his famous reflections on trusting trust. This is kind of once we get to late 80s, we get to this point where security starts to become a thing in C, and we start to see the ugly side of C. So if you talk to a bunch of people that did C programming in the 1980s, right, or even 1970s, they'll say stuff like, well, yeah, we knew where C programs could crash, and we knew that was a bug, and we'd go and fix the bug. But a lot of them, they didn't think about well, if I overflow the stack and I smash the state instruction point, it was a bug, right? It was a bug, and you'd fix it, right? But once you get into the late 80s, but that changed, right? In particular, when the Morris worm hit, and it exploited a buffer overflow, right? That's when the whole C security thing kind of really became a thing, right? That's kind of the starting point of that, right? And this is an excerpt of a 1988 paper by Gene Spafford, a write-up of the Mars worm. And this section in particular I really like because this very succinctly describes the finger buffer overflow. And it says, it was a specifically constructed string of 536 bytes passed through a daemon overflow and input buffer on parts of the stack. It was 4 BSD running on a VAX. Overflow resulted in return stack frame from the main routine being changed to the return address pointer to the buffer in the stack, right? So it pointed to a piece of shellcode, and this is the actual shellcode. This, by the way, is VAX assembly. It may look familiar because it's not that far off from Intel assembly, but if you look at it, it's like, okay, you push a string to the stack, move your stack pointer to R10, push 0, push R10, push 3, call a syscall, right? And what that really is 0, 0, 0, 0. R10 is the pointer to the stuff on the stack, so it's this guy. And then 3 is the number of arguments. And then 3b is the syscall number for execv, right? This is the shellcode for the Mars worm. It caused a lot of damage. We later started calling this eggshells when you get into the mid-90s and you read the Yellow 1 frac paper. But before that, this is just genius, right? This is, I don't know where Morse took his inspiration from, but this is beautiful. Anyway, another thing about C getting around is that we're no longer just talking Unix here, right? C gets everywhere. It gets all sorts of places, all sorts of operating systems, all sorts of applications, including like Windows NT started in 1988, 89. It was written in C. And I never expected to get a response, but I sent an email to Dave Cutler saying, hey, why did you write it in C, and do you think it was a good idea? And stunningly enough, Dave mailed me back, and he's like, well, we wrote it in C because it was the only reliable language at the time with a quality compiler and the features we needed to build an operating system, right? And then it goes on to say, we considered others like Ada, Modula, Pascal, but they either lack quality compilers or were grossly deficient in language features, which I think is beautiful. And then he says, looking back, we made the right choice. And I think he's right. I think they did make the right choice. And it totally makes sense, right? From everything he says, from sort of everything you look at history is like, yeah, at that time, with the compilers available, the features that language offered, it absolutely was the right choice. In fact, I think it was more or less the only choice. Anyway, that's now we get into the 90s. This is where the 90s is where I learned C. So it shows you how old I am. Younger than some of you in the audience, older than probably a fair amount of you in the audience. But anyway, C is where, this is where C starts to get a really, really bad reputation, right? Yes, more Unixes, more platforms, more C code everywhere. People start running their web servers in C. People for a while start writing web applications in C. CGI is written in C. Horrible, horrible, horrible idea. We should have never done that. It was a huge mistake. At least we learned that one. Although some of the embedded stuff still has web apps written in C. Again, huge, huge, huge mistake. Yeah, the 90s, when you talk about C, this is the rise of memory corruption bugs. This is where all bad things sort of start. When you look at, it's funny, because between the Mars worm, which is late 80s, up until 1995, there wasn't that much in terms of buffer overflows in C that was well known. There was one group that stood out, and again, this is not a presentation on like hacking groups and so on, but I have to mention them because not many people recognize this name these days, but they were incredibly, incredibly instrumental in moving the needle. It was a group called 8LGM. I think it was 2 or 3 British guys. They did some really, really groundbreaking stuff that was at least a decade ahead of its time. They wrote exploits and advisories, exploited buffer overflow, exploited a null pointer in the early 90s. Really, really groundbreaking stuff. If you haven't seen their advisories, I would highly, highly recommend you go read their stuff. It's really, really beautiful. Anyway, once we get to the mid-90s, people start looking at string-based buffer overflows, mostly on the stack. So most of the 90s or mid to late 90s, when you talk about C, it's buffer overflows, it's stack-based buffer overflows, it's string-based buffer overflows, right? Once we start getting to the late 90s, early 2000s, people are kind of waking up and saying, hold on. Like, okay, look, the string functions are just bad in C, okay? But we can fix this, right? And so you get the OpenBSD folks, and later some of the folks at Microsoft, although that gets into the 2000s, going, okay, string copy is bad, string cat is bad. Let's create string lcat, string lcopy, string ys, and so on and so on. And this definitely improved stuff. We certainly got, once this stuff was integrated well into application, people started using this. Yes, the trend for string-based, stack-based buffer overflows kind of went down. The other thing is, string-based, stack-based buffer overflows is really just a tiny fraction of all the horrible memory corruption things you can do in C. And once you get to the sort of late 90s, you get these first glimpses of heap-based buffer overflows, right? And then, right, the other thing we got in the 90s is the C99, right? C got standardized in 1988. C99 was a huge, big update. I'm still a C99 guy. I know there's C11, I know there's C17. To me, it's like they never existed. Like, I still write C99. And there's some interesting, once you get to the late 90s, these are sort of two people that actually did some secure C development at the time, recognizing just how terrible of a language it is for security. So Dan Bernstein, which is the author of DJB-DNS and QMail, does a whole bunch of crypto stuff, has a line on his webpage about the design of either DJB-DNS or QMail, I can't remember which one, but he says, I've mostly given up on this standard C library. Many of its facilities, particularly SDIO, seem designed to encourage bugs. And I think he's right. String copy, yes, printf, it gets all those APIs. I mean, they were fine in the 1970s when nobody cared about security and you're trying to bootstrap an OS. But by the time you get to the 90s, I mean, it's amateur hour, right? You can do better than these APIs. And Dan did. He did actually write a much better API, although not many people use it. And then similarly, Chris Evans, who's the author of VSFTPD, has a sort of more formalized set of sort of saying what Bernstein said, which is, all this sort of replicating strings and buffer sizes, bad idea. Creates his own secure string buffer, uses API, and it's worked for VSFTPD, right? It's had very, very, very few security issues, even though it's entirely written in C. Right, so now we're get to the 2000s. And this is where people really, security researchers, really put their foot to the pedal, and like we get format string bugs, we get heap overflows, we get integer overflows, we get exploitable little references, and the rest of the world goes like, oh, what the hell's going on? Let's at least, okay, if we can't fix C, can we at least try to treat some of the symptoms a little bit? Right, so this is where we get stack cookies and heap hardening and ASLR, and this is all sort of not trying to fix bugs, but saying like, okay, well, if you try to exploit something, we're going to make it difficult for you to exploit these things, right? And there's a really good presentation at Black Hat called The Almost Complete History of Memory Corruption Attacks, and this dives into a lot more detail than I did. And this goes up to about 2010 by a guy named Haroon Mir, I think. I highly recommend it. It's a really, really great paper. The other thing about 2000s is this is where optimizing compilers got really, really, really smart. And that too led to security bugs. There's a pattern here, right? So yeah, one kind of thing I want to mention is format string bugs. These were bug classes that were discovered, security bug class that was discovered around the year 2000. It led to memory corruption bugs. It was bad. It was also sort of inventive. It was like, oh, it was a new way of, it wasn't just a buffer overflow, it was something cute. But what was really cool about format string bugs is that they are easy to find. You can't do that many subtle variations. It always requires calling you some kind of function that you can grep for. And because of that, this, depending on which way you look at it, this may be good or bad. Format string bugs were hunted to extinction within about 2 years. You go, yay, as a security guy, like, great, no more format string bugs. There's a side effect here, which is if you find a problem and you eradicate the problem, but you don't prevent people from reintroducing this, is that as time goes by, people forget, right? So we killed format string bugs in 2000, and then new people come in, old people leave. Your new people don't know about format string bugs. It's 10 years later. They either don't know or they forget. You get more format string bugs. When we got sort of the first wave of iOS apps in 2008, 2009, 2010, every single one of them I looked at the time contained format string bugs. And it's because none of these folks knew what they were, and they reintroduced all these old bugs that we had long killed. You go, okay, well, that's an iOS thing, but the rest were good, right? Except, no, we're not, because people really do forget these things, right? There was a format string bug in OpenSSH last year. The unprivileged process could send a string to the privileged monitor. Privileged monitor would use it as a dynamic format string, and it would full-on format string bug. Luckily, it was a feature that was not turned on by default, but it was there. I think it was 8.5. I think it was either fixed in 8.5 or 8.6. I'm not quite sure. And there's more about format string bugs. It's not just that C has many bad security qualities. It's a carrier. It has infected other languages with its damn format string bugs. To some limited extent, you can have format string bugs in Go and in Python and in Perl and a few other languages. Not in Rust, though. But here's the one sort of cool thing about format string bugs. And this is why I love the C programming language, right? Why I say it's one of my favorite books. If you read it very, very carefully, this book was written in 1988. On page 155, you will see this. Let me highlight this. This is Dennis Ritchie going, okay, if you do this is the format string bug. Dennis Ritchie says, this fails if it contains a % sign. And then he says, this is what you're supposed to do. And he says, this is safe, right? So they knew. And they documented it, and people still didn't get it, right? And in fact, in 2004, I did a presentation on format string bugs, and I'd read the book, and I'd seen this, but I didn't have the first edition. And I actually emailed Dennis Ritchie, and I asked him, is it in the first edition? Because I want to know if it was published in 1988 or 1978, right? And to my surprise, Dennis mailed me back and said, and like 15 minutes later, like it was crazy. He said, we did not put it in the first edition, but we noticed that people were doing it wrong, kept doing it wrong, and that's why we put it in the second edition. And I wish I'd kept the email. I've long lost the email. I've been kicking myself for it ever since. But yeah, it's there, and it was there for a reason, and then everybody still ignored it. So now we're getting into sort of modern history, right? The 2010s. Yeah, basically more exploit mitigations, this time short petite. More exploit mitigations means more clever exploits, which means more exploit mitigations means, there's a pattern here, right? This means you get chain exploits, info leaks, clever attacks, and so on and so on. There's a pattern here. Basically, the problem is we keep treating the symptom. We do not deal with the underlying problem. Right? And then, yeah, there's standardization, right? We got C11, C17. But as I mentioned before, to me, the C standardization stopped at C99. Okay, cool. Okay, I've got a few more minutes. We're the last part, observations, conclusions, and maybe a call to action. So C has definitely inspired a bunch of languages. Anything written after, or almost any language written after 1970s will look somewhat C-like to some extent. Certainly C++, Java, C#, Go, Rust, Perl, Awk, I mean, all of them, right? I mean, the idea is this, right? They got the syntax right? There's distinct expressiveness of C in the syntax. They got that right, whereas everybody else before them didn't quite capture it as well as they did. And it shows, right? Almost every new language today borrows heavily from the C syntax. So why was it so successful, right? The success is, I mean, it's undeniable, right? C is ubiquitous, it's everywhere. It runs on an 8-bit microcontroller up to supercomputers, mainframes. It is everywhere. It runs on every platform and every OS. There's compilers for everything. It's easy, it's simple, it's powerful, it's expressive. It's you get access to the absolute raw power, almost all of it from assembly, in a portable, expressive way, in a very simple language, right? So this is where, like, C ended up with this, just by accident stumbled on this magic formula that allows developers to write low-level code in a fast and portable way. But it's really hard to exactly put your finger on exactly what it is. And I think it's really just a combination of things, right? It isn't one particular thing. I do think it helped that it was created for a practical sense and not like by committee. I think that had something to do with it. The last thing I think why C was so successful is because there's lots of compilers, right? This is also what echoed by Dave Cutler. If you don't have good compilers, the language is going to die, right? So I think that helped. The bad and the ugly. Well, we know this, but these are all the reasons why C sucks, right? It's like they did strings wrong. They did null pointers. Not really their fault. It was really 20 horn, but still null pointers suck. They didn't catch integer overflows. They got that one wrong. No implicit buffer bounds. They got that one wrong. Most variables are initialized by default. They got that one wrong. No types. I got that one wrong. Integer rules are totally broken in C. Again, not really their fault because everybody else integer rules are kind of broken too, but they got that one wrong too. So there's a long list of things that suck about C. This is where you get this balance, right? You have this incredibly powerful language that allows you to do all these things, but it has all of these flaws. And I think over time, the pros still outweigh the cons, but not that much anymore. I think every year the balance tips a little bit more. And I think we're at the point where it's about to flip the other way, and we need to move on. And these are just some numbers, right? So this is 2 days ago. I looked for CVEs for like C-related buffer overflows, right? 13,000 something, 7,000 memory corruption, 3,800 something heap overflows. And here's the thing: these numbers are stale. They're 2 days old. The numbers are higher today, and they're going to be higher tomorrow, and they're going to be higher day after that, and day after that, and day after that, right? They're only going to go up, right? And this is C. This is the problem with C, right? It's not going away. There's some stuff about compilers, but I run out of time, so I'm not going to do that. What's next? And I got 2 slides, and that's it. What's next? First thing is, and this hurts me because I love C. As a person who loves C, it hurts me to say this. It has served us really, really well for the last 50 years, but it's got to go. It's time it's come and go. It needs to go. We should not touch another C compiler, right? C needs to be relegated to that niche that is COBOL and Fortran and like old legacy stuff, right? The idea is if you are maintaining an old code base that's written in C, okay, you don't have to rewrite everything because that's a huge pain in the ass. But if you're writing a new program tomorrow, don't write it in C. It is not the right choice, right? If you think C is still the right choice, think long and hard and then pick something else. There's a new C standard coming out in 2023. I don't care. It's got to go. I don't care about it. I mean, and I hear people complain about it, and I have friends that are on the C standards committee, and I know they do cool work. This standard shouldn't happen. We should just move on. So then what's next, right? And there's a tweet from Mark Rustinovich, by the way, who echoes sort of my sentiment, let's not write new stuff in C and C++. He explicitly argues for Rust. I think Rust would be a good choice, but I don't think it has to be Rust, right? I think the new modern programming language that came out in the last decade or so, they have a lot of lessons learned, and they offer a lot of good alternatives to C. They may not be able to be like a quote-unquote C replacement where one size fits all, but I think depending on what it is you're using C for today or what you plan to use C for, you can find an alternative today and it'll have a good compiler. If you like Rust, go for Rust. If you want to write Go, do it in Go or Zig or Nim or V or Swift. And there's a lot of choices, and there's more coming. I was talking to a guy yesterday who made his own language called Hair, which is somewhat inspired by C and somewhat inspired by Rust, and somewhat inspired by Go, and has a bunch of its own little things. And it's if you don't want to write stuff in C, you could write it in Hair. Language isn't stable yet, but it's actually really cool. And I think I kind of twisted his arm to come talk here. So on the third day, we still have to put it in the schedule, but on the third day, he'll come talk here about hair. It's really exciting. Last thing I want to say is that, so the cool thing is that C has influenced all of these languages one way or another, right? This is the sort of influence part I was talking about earlier. They have filled the gaps that C was never able to fill, right? So implicit bound checks, all of these languages have implicit bound checks. No integer mixing, most of them don't have that. Null pointers still kind of a problem in some of these, null pointers can still bite you in the ass and go. You're good in Rust though, depends where you are. Not a fully solved problem yet in some languages, but we can't have everything all at the same time all the time, right? So anyway, strings don't have to be null terminated. Yes, thank God. Let's not do null terminated strings. I don't think any of these do that, except when they have to call system calls, obviously. But great, let's not have null terminated strings. Better supports abstraction and composability, right? This is one of the problems that C never tried to solve, but it's like why you shouldn't write web apps in C. It's not the right language for it, even if you didn't have the security things. It doesn't have the tools for abstraction and composability. Rust, Go, for sure, have much, much, much better tooling for those things. So anyway, my conclusion is essentially, it serves really well for years, let's get rid of it. Let's look at the modern language of the last 10 years for something that replaces C. With that is the end of my presentation. I have some references there. I think I know I ran a little bit over, but I think I have about 8 minutes for questions. 5? Okay, I have 5 minutes for questions. Does anybody have a question? There's one there. Awesome. Yes.
I have a question. So I think one of the reasons why C is still in such ubiquitous use is that a lot of industries have learned to depend on it. A lot of the tooling that is used by these industries is, made for C. How do we get rid of that?
That's a good question. There's no easy answer. I think you're right. I think it is true. There's awkward conversations. At some point, we're going to have to bite the bullet and say, how many more security bugs, how many more memory corruption vulnerabilities do you want to have, right? You have to make the case and say, let's be done with it. The other thing I think is you can make the argument for abstractions and composability. C is not very good at that stuff, right? So that I think even if you can't convince people on security, I think these are, from a non-security point of view, these are things C doesn't really offer, right? I think that's how you might be able to sell people on it. If they're not sold in the security argument, I think those are the arguments. But yeah, there's no easy path. It's going to be a pain in the ass. What is nice, it'll be slightly less painful because if you, the cool thing about C is that it's not very hard to do interop with C. It's hard to do interop with C++, but interop with C is relatively easy. I can call it the C code from Rust. I can call it the C code from Zig. I can call it the C code from Go. You can do it from most languages. If you export a function, I can call into it from most languages, right? So there's some of that helps, but ultimately, yeah, painful conversations and convince people to kind of bite the bullet and go for it. I wish I had a better answer. Any other questions?
I just wanted to say I really enjoyed your presentation, especially the story. It was very engrossing. So, but also I was wondering, for me coming from, writing, if you're reading machine code, it's moving to assembly is like, a magical step. And same thing with moving to C. It still feels on the metal, but it's, it feels like superpowers compared to, assembly. And I'm wondering if you ever anticipate, languages like Rust, taking that kind of low-level position as well.
Yeah, you're absolutely right. They are, from that perspective, Rust, certainly Go, it not only feels more high level, it is more high level, right? That's, I mean, it's the flip side. It's not having abstractions is good and bad, right? If you don't have many abstractions, you're going to be close to the metal, right? That's why C is very good at like doing low-level stuff. It's also why it's easy to understand C code. Like you don't even, I mean, if you don't necessarily need an assembler, you could look at C code and relatively easily usually translate it to assembly. I mean, it'd be a slow hand process, but it's not that very hard. Whereas if you look at Rust or Go and so on, they're more high level, they're more abstracted. It's a lot more work for the compiler. I think we're just gonna have to live with that. I mean, the only way to have a C-like language would be to have C and do what it already does, and we'll just be stuck with the same security problems. I don't know of any other way to do it. I'd love to hear ideas, but that's where I'm at right now. Cool. One last question, if anybody has one. Okay, well, with that, thank you for listening then.